Hello, today is Wednesday, October 27th, 2021, and I'm continuing with the video presentations. As I have mentioned in my earlier presentations, many of my talks have been backup material, backup presentations for the keynote addresses that I give, because just in case there is a technology glitch. And then there are also some other presentations that are on some important topics, research topics, and some presentations on some of the developments in cybersecurity and data science, even 20-25 years ago, because I'm a firm believer that you have to record history. History has to be recorded and stored so that, we can refer to it from time to time, and the generations to come can review these videos to sort of give them some idea as to what happened, because often I find that researchers and people usually reinvent the wheel. And so if something has been done before, it's always good to know about it so that you can build on that instead of sort of repeating what others have done, those who have come before you. And so I gave some presentations on, let's see, secure, multi-level secure databases, inference problem. And so today my talk is going to be on secure distributed database systems. And much of the work for this presentation was carried out in the 1990s. And I still use some of it because a lot of the work on cloud data management, web data management, and even web services, secure web services, was really built on top of the work that I'm going to present today. Okay, so I'm going to now share my screen. By the way, I'm Bhavani Thuraisingam from the University of Texas at Dallas, and I've recorded several presentations, many of them, at least, between 45 and 50, since the pandemic, and that was what, March of last year, March 2020. So since then, I've recorded several presentations. Before that, I just had the one presentation, which was recorded in 2008. So many of these presentations have been recorded since March of 2020. Okay, so now I'm going to share my screen. Okay, so the topic today, as I said, is security for distributed data management. Okay, security for distributed data management. So first I'll talk about distributed database systems, in particular, the architecture, data distribution, and functions. Then I'll talk about some security issues, in particular discretionary security and multi-level security. And then I will extend distributed databases to heterogeneous and federated database systems, and in particular security for heterogeneous and federated database systems. And my assumption is that the network is secure, right? So remember, when you distribute systems, there are multiple databases, homogeneous or heterogeneous, that are integrated. And so how are they integrated? Through some network. So I'm assuming the network is secure, so I'm not going to get into network security. So my focus is going to be on securing the data. And as I said, much of the work discussed in this presentation was carried out in the 1990s. However, this work lays the foundations for secure web and cloud data management, as well as secure web services. Okay. So what is distributed database systems, right? So you have database system 1 at site 1, database system 2 at site 2, database system 3 at site 3. So site 1 could be Dallas, site 2 could be Los Angeles, and site 3 could be New York City, right? So each database system is managing its own local database, database 1, database 2, database 3. And these database systems are connected through a communication network. And there is some module that connects all these database systems. And we call that module distributed processor. So there's a distributed processor 1 at site 1, distributed processor 2 at site 2, distributed processor 3 at site 3. If all these databases are homogeneous, that means essentially what we are saying is there's one massive database and we are not storing the entire database in one location. Especially in the 1990s, we didn't have the storage facilities we are having today. So the idea was to break up the data and store it in multiple sites. So if you have this big company, right, with branches in Dallas and Los Angeles and New York City, then you would store the data right next to the, in that site, local data. So employees in Dallas, they will have a local database. Employees in Los Angeles will have their own database, and employees in New York City will have their database, right? So you distribute the data because you want the data to be close to the, close to the employees. Okay, so the data is distributed. So in this case, I'm assuming there are two sites, site 1 and site 2. The employee data is distributed, right? So site 1 has got employee 1 with social security name, salary, department number, and site 2 has department 1 with department name, department number, and manager. Similarly, site 1 has a second second table, and site 2 also has the fragments, employee 2 and department 2. Right. So we are assuming that math and physics, these departments are maybe in Los Angeles, and computer science, English, and French in Dallas. But then we find there's a little bit of a problem in the sense that we are storing, not really a problem, but you can see some interesting observation. Physics department number 20, right? And there are none of the employees stored in site 2 are in physics. So actually John is in physics department, but he is in site 1, right? So this is not really an ideal situation because our whole idea was to keep the data right close to the people, which means, the site 2 should have the math and physics departments and all those in math and physics, because we got Jill in math, but she's not in site 2, she's stored in site 1. So we've not really, stored the data sort of close to the employees, right? So they are sort of stored in random. Sometimes you can use load balancing and store the data where there is storage space. So a number of things that you can do. Okay, so distributed functions, database functions, in particular, they include query processing. So you have query processing in central sites and query processing across databases, right? So when you query for all of the employee information from, say, Los Angeles, then it will have to go and query the data in Dallas, as well as in New York City, put all the data together and give it to the user. And so some of the research challenges at that time were optimization across the databases. Of course, you have to do distributed transactions, right? You may want to update, give an increase in salary to all of the employees. So some are stored in San Diego, some in, Los Angeles, some in New York, and some in Dallas. And so you carry out the transactions. All of the employees have to get an update, or none of them get an update, salary increase. So that's distributed concurrency control and recovery. And so again, a lot of research was done in the 1990s, even 1980s. So a lot of the distributed databases, security was carried out in the 1990s, but distributed databases, some of the work started in the late 1970s and went on 80s and 90s. So metadata management, how do you manage the metadata? That is data about data. So techniques for managing the distributed metadata, distributed security, and so that means the metadata also could be scattered, so whenever you add an attribute, delete an attribute, and so on, the metadata has to be updated across all the sites. I just want to make sure that, just a second, I just want to make sure that, just a second, that there is, okay, that the sound is still, just a second. Okay, we are fine, don't worry. Okay, so, and the last one here is security integrity maintenance, and that's what we're going to talk today, in particular security. Techniques for processing integrity constraints. That means that all the salary together for the employees, you cannot, because you're budgeted, say, only 1 million, so it cannot exceed 1 million. That means you've got to go and check all the salaries across all the databases, across all the distributed databases, and then make sure the integrity constraint is satisfied. And we will see access control rules also enforced across all the databases. Okay, so these are the distributed database functions. Now, secure distributed databases, we are assuming that each site has got a secure local database, database system, managing its local data. And then our distributed processor now becomes a secure distributed processor, right? So security is incorporated across all the functions. And then, of course, you have a secure network connecting all the databases. Okay, so what are the functions? Okay, discretionary security. We have got discretionary security, mandatory security. So if you listen to some of my earlier presentations in central databases, we talked about access control for database systems as well as multi-level secure database systems, right? So discretionary security, we have got access control and authorization policies enforced across all the databases, administration policies enforced across all the databases. And then, of course, you've got identification and authentication, because you can be in Los Angeles and identify and authenticate, but you've got to make sure that you're authenticated so that you can access the remote databases as well. Okay, so these are some of the security mechanisms. And so the policy integration, remember, you have policies across all the local databases could have their own policies as well, right? When you talk about homogeneous, then the policies are more or less the same, but sometimes you might have added restrictions depending on the state, because Los Angeles is in California, Dallas is in Texas, and New York City is in New York State, right? So you have security policy for database system A and system B and system C, and they all have to be integrated. Okay, so don't worry about this, this particular thing. There's no white, there's no particular significance. It's just that I copied this from some of the earlier presentations and papers that I wrote. It's from my work and my team's work. And so when I copied it, I don't think the white part copied properly. So just ignore that. So you can say, you can also create views. So you have employee 1 at site 1, department 1, also site 1, employee 2 and department 2 at site 2, but you want to form a employee department view, and again all those who work in the physics department. So it looks like although physics department information is in site 2, people in the physics department, let's see, all right, yes, one of them is in site 2, and we also have one person in site 1, right? So if you want to form a view of the people in the physics department, I don't know whether I formed it correctly. Of course, there are 2 people. No, physics, no, this is a salary, sorry. Physics is number 20, okay? The physics department is number 20, I made a mistake. So number 20 is physics. I looked at the salaries here, so forget about salaries. We're looking at departments. 20 is physics. So there's no one in site 2, but there are some people in the physics department. They all may be taking the course remotely. So there's John, and then there is what? Physics is number 20. So there is not John, there's Paul, and there's James, and there's Jill. Wow, there's Jane. 4 people in physics all happen to be in site 1. Okay, and if you form a view, you get Paul, James, Jill, Jane. That's the views for security. Okay, so secure distributed database functions, when you bring security into this. Query processing, of course, we have to enforce access control rules during query processing, like query modification, which I mentioned in my earlier presentations, across the databases, right? So query is modified, so all the queries are modified according to policies. The modified queries are posted in the local databases. The results are obtained and given to the user. There's also distributed inference control. We remember, I think I did talk about inference in distributed database systems in one of my presentations. So what happens here is that you can have one piece of information in site 1, another piece of information in site 2, like healthcare records and some other information. You put it together, it could be highly classified or highly private. And so these disparate pieces of information or different records are stored in different sites. You've got to put it together and make sure that there are no unauthorized inferences. And of course, there is query optimization and so on. Then transaction management, there could be security constraints also during policies, during transaction processing, right? Because you have a part of the transaction in site 1, there could be some security policies governing, say, California, some other security policies governing Texas, but both transactions have to, sub-transactions have to be executed, or none have to be executed, right? Metadata management, again, you enforce access control on the distributed metadata, because your metadata, that's data about the data, that could be distributed. Integrity management, again, ensure integrity of the data is maintained while enforcing security across the databases, right? So everything here you are looking at, enforcing across the different databases. Okay, so now we go into multi-level security. Remember, in a multi-level secure system, users are cleared at different sensitivity levels, and data is assigned different security levels, and user has clearance levels, data has sensitivity levels, and users read the data usually at or below their level. When you enforce the Bella Padula, they write data at their level. Bella Padula says at or above your level, but we are saying you write data at your level. So you have different multi-level secure processors each side. You have a multi-level database system. Each system is managing its own multi-level database. And of course, you have a multi-level secure network. That's the architecture. So what we do here is that we are saying site 1, you have an employee table that is secret, and don't worry about the white part not getting copied here, okay? No significance. Department 1 is all unclassified. Employee 2 again is secret. Department 2 is unclassified. So unclassified people can read only information in the department. Those who are cleared as secret can read information both in departments as well as in employee tables. Okay, so that's a multi-level relational data model. And then multi-level distributed database system functions. Remember, we talked about a distributed processor, right? So functions of a multi-level distributed data system is you have site A and site B, and then you have a peer-to-peer communication. The distributed processors or query processors will communicate, the transaction processors will communicate, the metadata managers will communicate across the sites. But again, remember, we are assuming that these are all security versions. That means security has to be maintained. Okay, so now we have, I think I talked about it in one of my earlier presentations, distributed inference controller. So again, you have got 3 sites, 3 database systems managing their own local databases. So you have a local inference controller. In my earlier picture, I think I showed you, they manage the local inferences, right? And then distributed inference controller. So once you sanitize all of this data, then this distributed inference controller will communicate with its peers and see, is there any information at the other sites, right? So for example, you have some medical records here and some other information, but if you can put it together, then you can identify, like maybe some address information. So if you can connect all this, you can identify the person, which you don't want, right? So that's what the distributed inference controllers will look at, information across the sites and decide whether there is any unauthorized information is being inferred because the data is distributed. Okay, so now we finish one part of it. Remember, so up until this point, I've assumed that the database is homogeneous, right? You've got the same tables across and so on, across the sites. So essentially homogeneous. The reason is that you have got this one massive database, and we are assuming that we can't store everything in one site. So we are distributing the data, right? And remember, when we talk about 70s, 80s, 90s, we didn't really have that much storage. We never talked about the cloud. We didn't have the web at that time. Of course, in the 90s, we had the web, but not so much in the early 1990s. And so we said, or the thought was, not just we, the community, that you want to fragment the data and store it in different sites. So database A, system B, and system C. Transparent access to heterogeneous databases, both users and applications. So, okay, so now what we are saying is in this chart, okay, it's not the homogeneous data that we have distributed, but what's happening here, because of mergers and acquisitions with different companies, each company could have its own database, right? So remember, we had what, Informix and IBM acquired Informix, right? So database system A is relational, that's Informix's database. Database system B, maybe some other object company also merged, let's say. So company A is relational, company B is object oriented. And remember, IBM has still, it operates fully functional hierarchical system. IBM has DB2, which is relational, but yes, they have their IMS system, which is hierarchical. And so these three companies are merging, or in this case, IBM is acquiring, let's say, the other two companies. And so what happens here, right, is that these databases have to be integrated. At that time, it was a huge challenge. We are talking about the early 1990s, where we talked about interoperability between heterogeneous database systems. Okay, so of course, today that this problem is solved, more or less solved, and I'll tell you why. But let's again, right now we are still in the 1990s. Okay, so heterogeneity could be with respect to data models, which is what I showed earlier, right? Relational, object, and hierarchical. Schema, that's the metadata, query processing, query languages. One could be SQL, IMS could have its own language, transaction, semantics, integrity, different security policies. So that is heterogeneity, right? Different databases. Federated, some of the databases or some sites could form a federation, right? So where they want to cooperate, right? So for instance, United States is part of NATO, but it's also part of what used to be NAFTA. I don't know what there's a new term now for NAFTA. So it's part of the North American free trade agreement or whatever, right? Free trade agreement between, I think, Mexico and United States and Canada. And it's also part of the NATO, which is what, UK and France and Germany and so on. So it's part of two federations, right? Similarly, UK is part of the Commonwealth, right? But it was not now, but once upon a time, right, until January 31st of last year, 2020, it was part of the European Union, right? Two federations. So some organizations want to cooperate, although they have different databases, they want to cooperate and work together, but collection of cooperating, but they also want to have their own autonomy and possibly heterogeneous component databases, each belonging to one or more federations. So that became a really big thing at the time. And then at that time, we also started talking about client-server architectures, right? Interoperability based on client-server systems. And today we still have all of this, but right, the cloud and the web have sort of dominated all of this today. But the technology is, by the way, whatever I'm going to discuss, it's still there, okay? Okay, so federated databases, I'm saying A and B are forming a federation and working together. They're cooperating, but still they have some degree of autonomy. And B and C are forming a federation F2. Okay, so one of the things, and this is a famous paper by Amit Sheth and Jim Larson. Amit Sheth, I think some of this work was done when he was at Honeywell. He was my colleague. I was in the security database security group, and he worked on the heterogeneous database integration with Jim Larson. And so it was published in ACM Computing Survey, September 1990. It has got thousands and thousands of citations. Okay, so what they said was, and remember, what I did for this work was incorporating security into this picture. Okay, this is their work. So they said you have three components, right? A, B, and C. Right, they have their component schema. So we said A was relational, B was object, C was what? IMS, I said, right? Hierarchical. And then you have a generic schema, that is the metadata in some common language. At that time, we said, okay, let's go with objects, right? Object language, because object is generic enough, it can encompass everything, right? But today, no, I'll tell you what we will do today. So then this system is exporting some to its federation. Remember, A and B are forming a federation. So they don't want to export everything to their federation. They are exporting some of it, component A, And then from component A, some of the metadata that they want to expose to the foreign organization. Similarly, B exports something. And then these two together will form a federated schema. And then for the external users, different depending on the user classes, you have, again, a subset of the schema, external schema 1.1 and 1.2 for this federation 1. For the second federation, remember, B is part of the second federation. So you have the generic schemas as before, but it's exporting something else to the second federation. And C exports some schema from its schema. And then you have the federated schema for the second federation. And then you have external schemas 2.1 and 2.2. Okay, so the generic schema is really the technical challenge, right? Coming up with the generic schema. So at that time we said, let's go with object-oriented, right? So I did this work, I believe, in the around 90, right? Yes, 91, 92. Their paper came out in 1990. So I looked at security for federated systems. I wrote a report, I think in 91 or 92 for one of my projects. So at that time I said, let's go with objects. But today, we are in a great situation because we have a common language, just like we use English to speak with everyone, right? In the world, English has become more or less the universal language. In the computer terminology, XML, extensible markup language, has become sort of the common language, right? For data representations, because almost anything can be represented using XML. Right, so you have this generic schemas are all represented in XML. Here you have relational, and then you have objects, and then you have hierarchical structures, but everything is represented in XML, and then you are exporting everything in XML. Up to this point, I believe it would be XML, and then the external schemas, depending on the users you want to use it, right? This may not be in XML, depending on the different user classes. Okay. So that's the schema integration. And then we looked at security. So, right, just a second. Do I talk about security? Yes. I'm going to discuss security, okay? So then the client-server example is that you have, again, the whole idea here is that you have any client accessing any databases through the network. So you have a client from vendor A, client from vendor B, network, you have a vendor C server, a vendor D server, right? And then databases. The idea is transparently A accessing this database or B accessing this database or whatever. Okay, so there was a lot of interest about 20 years ago. There was a lot of interest in this architecture. But then later on, we had technologies like by 96, 95, 96, we had technologies like JDBC, Java Database Connectivity. We had ODBC, and I think ODBC was a Microsoft product, I believe, at the time, right? At that time, a standard. And so ODBC, JDBC, these are the standards that were developed to connect clients to various databases. Okay, so there was a lot of work in this area as well. Okay, so now what are the security aspects? So when you transfer the data models, transform the data models, you need to look at all the security properties, right? If you have access control in a relational data, like employee table like John cannot access employee tables, then when you have the generic schema in XML or objects, John still cannot access whatever is equivalent to the employee table. So those security properties must be maintained. So security architectures, heterogeneous and federated data management, and then of course there's security impact on schema data policy integration. I'm going to talk about every single topic. And then you can have something really strange, incomparable and overlapping security levels. I'll mention what I mean. Inference control, of course, secure client-server computing. Okay, so transforming data models. So remember at that time we said everything is transformed into objects. So when you transform tables to objects, the table here, employee tables becomes employee class, which is secret. And we have John, J, Paul, and Mary. These are the tuples, but they become object instances. And here you have department. And then we have a level here. Department is multi-level, right? In the sense that we have math department is unclassified, physics department is confidential. So department class on the whole is unclassified, but it has two instances. Math is unclassified and physics is confidential. So when you transform these data models, the security properties have to be preserved. Okay, so just like earlier, I said integrating distributed databases securely. Similarly, you have heterogeneous database systems, but then site 1 has got secure database system 1, secure database system 2 is site 2, and site 3 has secure database system 3, and they have got secure databases 1, 2, and 3. Of course, they are all connected through this secure heterogeneous distributed processor. They handle all aspects of heterogeneity, and they are connected through a secure network. Okay, so now similarly for federated, we said secure database 1, 2, and 3, secure database systems 1, 2, and 3. Instead of a distributed processor, secure distributed processor, we have secure federated processor, where it's also, in addition to handling all of these functions, it also has to handle federations. Okay, so what do we mean by federations? Policies have to be integrated, right? So we have A, B, and C. A has got its, we said, let's see, in this case, no. Okay, so in this case, we are using, it's a little bit different though, in the sense that we are not saying A and B form a federation, B and C form a federation in our example. All we are saying in this example is A, B, and C, all three together form a federation. So component A has got some policies, their agency A, component B has got its own policies, component C has got its own policies, and then you have to export. So first of all, you need a generic policy. I haven't shown in this figure, right? The generic policies could be in objects, specific, because if a generic schema is objects, then our generic policies have to be specified on objects. If it's XML, the policies on XML. And then we also, A will export some policies for the federation. Of course, these policies will have to be more stringent, just like we showed. Remember, here we exported data, right, to the federations. Instead, here we are exporting policies. So what this means is that we are more stringent. Our local users can access all of this data, and the policies are maybe less stringent, but for the foreign people, it's more stringent. That means, say, this is US. So we did a project, US, UK, and Italy, 3 universities. And so we said harsher policies for B2 access. Harsher means more stringent policies, and less stringent for the local, right? More stringent for Italy and for UK. And then all 3 are forming a federation, working together, but each one has got some autonomy. And we implemented this, and then we implemented this whole thing in a cloud. And I believe I did talk about it in one of my earlier lectures. Okay, now incomparable levels is very, very, very interesting, okay? Because let's say we have 2 sites, A and B, confidential and unclassified, right? A can handle only data, is accredited to handle data that's unclassified or confidential. B is accredited only to handle data that is secret or top secret. But still, they have to talk to each other sometimes. In some very strict cases, they will say, no, you cannot talk. However, they might be able to communicate through a trusted person. So in general, what happens in the real world, when they want to exchange data, a trusted person will look at all of the secret data and see, okay, is there anything that I cannot share here? So downgrade it and send it to this person, okay? Hand carry it. But we can do it with a trusted processor called a trusted guard. And these guards were developed in the 80s and 90s. And so, because remember, confidential and secret, although data can flow up, remember Bella Padula is saying you can write above, but you cannot write down. Similarly, you can read at or below your level, but you cannot read up. So someone from here cannot read here. And then someone from here cannot send data here. You can send data up, but you cannot send data down. So from unclassified, you can send data to confidential. This is like writing, right? Send data to the confidential level, but confidential data cannot go down. You cannot go down. So, but then confidential data talking to secret data is fine. You can go this way, but from secret data coming to confidential data, no. Right? You cannot write down. So what happens? It has to go through a trusted guard. Trusted guard is going to check everything. And if it's, it can throw away some things and send limited information to the confidential. So that's what we mean by incomparable levels. if we had a common security level, so if site A, node A had been able to handle secret data, then unclassified could move up to confidential, right? Because you can write up, confidential can move up to secret, and then secret and secret can communicate, right? So at the secret level, they can decide what data to send down, because you cannot write down. So whenever you write down, it has to go through a trusted guard. Okay, so secret data, you can write it up to a top secret. So that's how you could handle the incomparable levels. Okay, now, okay, so that's incomparable. Now I said overlapping. Remember, overlapping means there's secret, which is, I sort of spoke ahead. That was the next chart. So both sides can handle secret, which is good because unclassified data, it can move up to confidential, right? Because you can always write up. Confidential data can move up to secret, and secret can talk to each other. And then the secret data move up to top secret. Okay, so in this case, there is not a problem because there's an overlapping security level. Okay, so then, okay, for inference control, again, federated inference controllers or heterogeneous, you have component sort of agency A, B, and C. A has its local inference controller, B has its local inference controller, C has its local inference controller. And then some of the results you can export. It's an export engine. You can export to the federation. Maybe not all of the results, only some of them you want to share with your partners. And then it goes to the federated data management. And then on top of it, you take all of this data together, integrate, and then a federated inference, you check for inferences, unauthorized inferences, and then send the data to the user. So this was the federated. Today, we have implemented a form of this in the cloud. And I also talked about it in one of my earlier lectures. Okay, that's inference control. Okay, so secure client server computing, and again, back in the 1990s, huge development, which was three-tier architecture. And we still use a form of three-tier architecture, but now it's, then we started with objects for integration. That was in the 1990s and 2000s. And now we have moved to the cloud. So what happens with the three-tier architecture, which is very, very popular, you have secure clients and secure servers, and then a lot of the other functions like enforcing schemas or schema integration and policy enforcements, they all happen in the middle tier, right? So you can look at it as a collection of objects. And in fact, when I talk about secure object data management, I'm going to talk about how you can encapsulate each of these clients and each of these middle tier components, schema integration, policy enforcement, all of the servers as objects, and objects are talking to each other. So instead of putting a lot of burden on the clients or maybe even on the servers, you have got the middle tier, which is performing specific functions like schema enforcement or schema integration. So it's actually schema integration and policy enforcement. Okay, that's secure client server computing. So this is my last chart, which is directions. So I sort of gave you a broad overview. Techniques for centralized data management have to be extended, right, to a distributed heterogeneous federated environment. So that was what I talked about, right? Centralized means you have one central database and the query processor, update processor, everything in the central database management system. Now we are distributing it to across the sites. Summary and directions, by the way. And then I talked about access control enforced across databases. I also talked about inference control across databases. And I also mentioned heterogeneous and federated databases. And then web will continue to have an impact, and development of secure distributed data management, because everything has moved to the web now. And of course, network security is critical. You can't say network security is somebody else's problem. Make sure that the network is secure, because if your network is secure, forget about having a secure distributed database system. Of course, next steps, and we are already there today because this was in the 1990s, is secure web, right? That was sort of in the late 1990s and the early 2000s and continuing today. Of course, now we have got cloud data management and security, and I talked about that. So we've done a lot of work on secure web data management, secure cloud data management, secure web services. And in fact, I've written books on all of these topics. And now, of course, the next big thing is integrating cybersecurity and machine learning and also IoT, Internet of Things, and how do you manage all of this data, right? And that's where we are today. Okay, so I'm going to stop sharing now. And so this was again, as I said, I'm talking about things, going back in history, because I want a place to sort of record, all of this information that we have, right? It's always good because it's not just for me, it's also for the generations to come, not for my students today, also for my students, our students in the future, not just today or tomorrow, maybe 5, 10, 15, 20, who knows, 20 years down the road, somebody could review this presentation and said, okay, once upon a time, there was a lady called Dr. Bhavani Thuraisingam who gave this presentation. They might think this is really ancient when we look at some of the stuff that's written in the 1800s, who knows, right? Or they might think, oh, wow, this is something that's very relevant for me today, right? Who knows? But it's always good to share information. That's my goal, right? Share all of the information. And by the way, I also wanted to mention that a lot of the stuff that I have been discussing today, some of it I started when I was at Honeywell. That's where I started my career in 1985, my cybersecurity career, cybersecurity and data science in 1985. And then I joined the MITRE Corporation in 1989, January. And I was there since 2004, October. So 13 years, the last 3 I spent at National Science Foundation. But much of this work, probably 95% of this work was done when I was at MITRE Corporation. And that was throughout the 1990s. And so I'd like to also acknowledge the MITRE Corporation and also all of this work that I described. I mean, we have published, and so I've taken from various published materials in order to present this. And remember, whatever knowledge that we gain, right, it's never going to go waste, right? So we always must not just, we have to look at the present and the future. But they say, don't think about the past. But in certain things, we have to think about the past, what has been done, because I don't think we should reinvent the wheel. Sorry, reinvent the wheel, right? So that's important. And that was, as I said, that's the main reason I'm making these presentations. Some are very current, some are some of the current keynote talks that I'm giving, and some are sort of for historical purposes that I'm making these recorded video presentations, okay? And again, thank you very much for listening, and stay tuned for some more videos that I will be recording in the near future. Thank you very much and have a good evening. And now I'm going to stop recording.